Hello everyone, this is Marwa Taguti from the Deutsche Telekom Chair of Communication Networks, and today's talk is about compressed sensing. So let's start with a contemporary paradox where we have one raw image of size 15 megabytes to the left and an image of size 150 kilobytes. Obviously both of them look similar, and this shows that the massive data acquisition that we are having seems to be enormously wasteful, and most of the data is somehow redundant and can be easily withdrawn. So taking this example into an analytical problem, our first image could be modeled as a vector X that is projected using a matrix A that has less rows than columns to obtain the right image Y. Here the task is to recover X, knowing that there are more unknowns than equations. And this is what we call an underdetermined linear system of equation that the main theorem in algebra cannot actually solve, because we know that we need at least as many equations as unknowns. Here it is not the case. We have incomplete information, therefore we are asking if reconstruction is even possible, and how to get an estimation of the signal from this number of measurements m. So reformulating or going deeper into trying to solve this problem that we previously showed, actually we can rewrite it as an optimization problem where we would like to minimize X or find the sparsest solution X subject to the previous equation Y equals AX. The compressed sensing theory asserts that a signal X could be recovered exactly from far few samples or measurements compared with the traditional methods, where the number of measurements is really low compared to the original size of the signal in question. But here there is no magic compared to the linear algebra in general. You cannot really solve this problem unless you have some components. So to find a solution to the compressed sensing, you need to have a sparse signal, and you need to satisfy certain property. The matrix A need to satisfy certain property of incoherence or restricted isometry property, and so on and so forth. There are different types of properties that could be read about in the compressed sensing chapter in the book. So what can we really expect from compressed sensing? What can it do to us? What can it achieve for us? It provides a disruptive approach to data acquisition. This means that we are overcoming the problem or the limitation of the Nyquist theory that is limited by the bandwidth. Here, compressed sensing is limited by the signal structure, and we are overcoming the burden of the linear algebra. This is relaxed thanks to the sparsity of the signals, thanks to the proper choice of the matrix A, and so on. And compressed sensing guarantees that exact reconstruction of sparse signals from small numbers could be actually possible. However, this problem is not new. This problem is existent for a long time ago. But the problem was the L0 minimization. This means trying to find the support for the signal is the problem. It's actually an NP-hard, and as the signals get larger, this becomes really unpractical. That's when Professor Candace came with the proposal for compressed sensing, and he advocated that the L1 norm could be equivalent to the L0 in a technical sense. And in this way, we are moving from calculating a support to calculating the sum of absolute values of a signal. So this good approximation, this could be a good approximation to use a solution for the corresponding L1 optimization problem. And here we are trying to find the values of all the coefficients where the L1 norm, or the sum of absolute values for the signal X, is the smallest possible. There is a common algorithm for that is older than the compressed sensing theory itself, which is called the basis pursuit. It is an L1 minimization strategy that consists in solving a convex optimization problem, where we would like to minimize, as I said a bit earlier, X subject to Y equals AX. But still, this is good. The problem is somehow leveraged, but this still relies on linear programming to solve, and the basis pursuit complexity is cubic. And of course, the larger the signal, the more difficult or impractical it gets. So we need to find some alternatives for it. But first of all, let us talk a bit about this sparsity. We know that the real-world signals, they are really actually not exactly sparse. And in practice, you cannot have this strong constraint to impose. You need a weaker concept to make this compressed sensing possible. The good thing is that compressibility is actually, which is a weaker concept, is actually still valid, and it works really good. So to understand a little bit the difference between sparse and compressible signal, let's look at the graph, where on the y-axis we have the absolute values of the readings of, the components of the signal X, and on the x-axis we have the dimension of the signal. So a sparse signal, a k-sparse signal, has exactly k non-zero values, and that explains with the blue curve, and from k to the n components we have the amplitude 0. However, a compressible signal could be following, or is following, a power law decay, and even though sometimes we are not having 0 values, but we are actually close to it. And these signals can be well approximated by sparse signals. As for the basic reconstruction algorithms, we need alternatives, obviously, for basis pursuit, and it's interesting that up to date we cannot count the number of algorithms available for compressed sensing. It's extremely huge. That's what pushed some researchers to make major classification. And this is dependent on the type of the application, the signal, and many other parameters. So we chose to talk about or to show some of the common approaches that are used for compressed sensing. First one is the convex relaxation, the one we discussed about earlier, the basis pursuit. There is also the common lasso algorithm. There are also some greedy pursuits, which are fast algorithms, like the orthogonal match and pursuit. a thresholding based algorithm like iterative hard or soft thresholding, and finally message passing with approximate match and pursuit, or even the belief propagation proposed previously for LDPC codes. So in this jungle of the reconstruction algorithms available, one should be really careful on choosing the right one for its application, and this is based on, for example, the system's specification, the tolerance to errors, the recovery speed, or number of available measurements, etc. And in the following table, we have some very common and used algorithm, and along with their complexities and the number of measurements, and you could see that a basis pursuit complexity is a little bit too much compared to the compressive sampling algorithm. But the number of measurements of all of them is not quite different. So now getting to obtaining a sparse signal. So in general, we've been saying that like the natural signals or in signals that are in nature are usually sparse. If we talk about temperature, don't expect us to talk about zeros and a few values that are different from zeros. That is not correct. A signal, when we say a sparse signal, this means that this signal can admit a sparse or compressible representation in a different, using a proper basis. For example, if we have a signal x, it can be written as a psi, which is this transform or a transform matrix, and the theta, which is a k-sparse vector. Here there is no magic. It's a normal inner product calculations that we get, and the energy of the signal x can somehow be contained in this vector theta and the matrix psi. Amongst the transform examples, we could mention the Fourier, wavelet, discrete cosine transform, or also the Gabor filters. And for example, the discrete cosine transform provides a very good sparse representation for images, ECG readings, humidity, temperature, etc. This is good, but this doesn't provide an answer to all types of signals, and this comes to put a limitation for this fixed transform and the need for having a different, wider, more complete way of obtaining sparse signals, which is dictionaries. And these dictionaries are nothing than a generalization to transforms that we need to train ourselves. Okay, so just to show an example, this is an image where the left image was actually reconstructed, was sparsified using a wavelet transform and reconstructed on the right using only 2.5% of the coefficients that the original image has. And as everybody could notice, there is absolutely no visible change. So now about the dictionary learning, the task is to find the best overcomplete dictionary that we call D using a set of training samples X. So here we are no longer talking about a one dimension signal, but we are talking about a set of signals. So the one we were talking about earlier was X. Here we have X, X1, and so on until XL. We need this set of samples in order to be able to train it in a way that we could obtain this dictionary along with a sparse representation, along with the sparse representation. And this can be seen with the optimization problem in the slide. And amongst all the available algorithms, the most successful one was the KSVD algorithm, which is a generalization to the k-mean clustering, and it uses the singular value decomposition and the orthogonal match and pursuit algorithm. And the steps is to really alternate between fine and a sparse approximation of the training vector, while iteratively updating these columns of the dictionary to better fit the data until we finish the number of iterations that we set beforehand, or we reach a certain convergence. So now that compressed sensing imposed itself to be friendly in having the potential in being applicable on different types of data, it has imposed itself therefore to be applied in different applications, such as technological applications from single pixel camera, medical imaging, also scientific motivations, especially for my personal flavor for research, like sampling theory, sparse approximation, or machine learning. Additionally to theoretical extensions like matrix completion. So moving to the relationship between compressed sensing being a signal processing tool and a communication and storage issue. Now, currently, in our factories, in our cars, in our IoT devices, they are full and loaded of sensors which are instantly collecting data, and this is called data-rich information 4, and we are hitting a big data issue here. And with this irreversible explosion of big data in sensor networks, we need to we have the duty to greening these big data from the very beginning, from the stage of the data collection, and this can be done using compressed sensing, and also in the network. We can use compressed sensing to reduce the data communicated, reduce the traffic and the bandwidth usage. And knowing that the compressed sensing has the ability to deal with any type of data, and that the reconstruction algorithms, we have plenty of reconstruction algorithms which are actually stable, flexible, scalable, etc. This actually widens the potential applications for compressed sensing. So the takeaway conditions that I personally insist on reminding each time we talk about compressed sensing is that nothing is impossible, and compressed sensing could be applied anywhere as long as you could follow these steps, or you are somehow fulfilling these steps. So the first one is the problem of a sparse signal. If the signal is not sparse, it's not a problem. We can find a sparse representation in a different transform. If we don't have a pre-existent transform that could match my signal, no problem. We can train an overcomplete dictionary, and On top of that, if the signal is not exactly sparse, still compressible signals work as well. So the problem with the sparsity, we shouldn't talk about anymore. Another thing is that this matrix A needs to obey a certain property, but these properties to check, they are also NP-hard. The solution to that, simply use a random Gaussian or a Bernoulli matrix, and they can be as good as, and they are obeying these properties with a very overwhelming probability. Also, make sure that the number of measurements is smaller than the number of or the size of the signal itself, and of course the sparsity of the signal is lower than the number of measurements. So moving to a hands-on on compressed sensing in the CompNets emulator, we take a very small example here that you could try yourself in chapter 22. Very basic. We take a node S that compresses its temperature readings using once a DCT, and another time a trained dictionary that we obtained using these specific temperature data, and we would like to transmit it to a sink. This sink reconstructs the data using the OMP algorithm. In order to run the example, you could use the following commands. And as for the output, let's jump directly to the mean squared error result that we obtain when you use a trained dictionary. Here we have a 0.17 for MSE, whereas for DCT we have a 1.45 MSE, and this is not this is a very well expected result, as DCT as the dictionary was faithfully designed or trained to sparsify the data, and therefore it can help to have better results compared with the standard or predefined DCT transform. Thank you very much. You could check more details and learn more about the topic in chapter 10 and chapter 22 in the CompNets book. Thank you.